Welcome to The Explainer. Today, we're going to dive into something that's at the heart of all modern technology. How do we actually teach an artificial intelligence how to think? All right, so let's get into it. We hear the term AI learning thrown around all the time, right? But it's not like a person just cracking open a textbook. It's this really fascinating and honestly incredibly challenging process of trial and error and a whole lot of optimization. So let's break down what's really going on under the hood. Think of it this way. Training a neural network is kind of like sending it through a gauntlet. Yeah, the goal is crystal clear, but the path to get there, it is just littered with traps and challenges that can completely derail the whole thing. And here's the most important thing to get your head around. Everything, and I mean everything we call learning in AI, it all boils down to one simple goal: minimizing an error score. We call this score the loss. Literally every single adjustment the AI makes is just trying to nudge that one number as close to zero as it can possibly get. But right out of the gate, we hit our first huge trap. It's a massive balancing act. On one hand, you've got this thing called overfitting. This is where the model is like a student who just memorizes the answers for a test, but doesn't actually understand any of the concepts. So yeah, it aces that one test, but give it a new question, it completely bombs. Then on the other side, you've got underfitting, where the model is just, it's too simple to even learn the basic lesson. The whole game is trying to find that perfect sweet spot right in the middle. So the big question is, how do we get through this gauntlet? Well, we have this whole toolkit for exploring what we call the error landscape. I want you to picture a huge, hilly terrain, right? And somewhere in that terrain is the lowest possible valley. That valley is our goal. That's the point of minimum error. So how do we find our way down? Okay, our main tool for this job is something called gradient descent. The best way to think about it is like you're on a hill in the dark and you want to get to the bottom. What do? You feel around with your foot for the direction that goes down the steepest, and you take a small step. That's it. At every point, the algorithm calculates the gradient. That's just a fancy word for the slope of the steepest descent. And then it takes a little step in the exact opposite direction. This whole loop of calculating the error and then sending that information backward to tweak the weights, that's a process called backpropagation. It is the engine that drives all of this learning. Now, this process comes with a really critical trade-off. We could use the entire dataset to calculate our next step. That's super stable, but oh my god, it is incredibly slow. Or we could go to the other extreme and use just one single data point at a time. That's called stochastic gradient descent, or SGD. It's way faster, but it can be really noisy and jump all over the place. So the modern compromise, the one most people use, is called mini-batch. It gives us a nice balance between speed and stability. But there's a problem. Sometimes this step-by-step process can get stuck in a little ditch, a shallow valley that isn't the real bottom. So how do we fix that? We add momentum. It's exactly like a ball rolling down a hill. Its own momentum helps it power right over any small bumps and stay on course for the true deep valley we're looking for. And that idea brings us to the modern champion of all optimizers, ADAM. The name stands for Adaptive Momentum Estimation, and its big genius was combining that idea of momentum with something called adaptive learning rates. Basically, it automated the super tedious job of figuring out how big each step should be. It's smart. It knows to take big, confident leaps when the path downhill is clear, and then switch to small, careful baby steps when it gets close to the bottom. And, the results really speak for themselves. Because of this adaptive approach, ADAM doesn't just get to a solution way faster than the standard methods. It often finds a better solution, a point of even lower error in the end. There's a reason it's pretty much the default choice for everyone these days. Okay, but even with an amazing optimizer like ADAM, these powerful models can still find a way to cheat. They can just memorize the training data. So how do we stop that? How do we force them to actually learn and to generalize to new stuff? The root of the problem is this thing called neuron coadaptation. Basically, the neurons become codependent. It's the perfect analogy for that lazy group project in school, where a couple of neurons do all the real work and the others just kind of coast, relying on them. And that makes the whole network really brittle. It can't handle anything it hasn't seen before. So the solution is surprisingly direct and, honestly, a little chaotic. For every single piece of training data we show it, we randomly fire about half of the neurons. This technique is called dropout. And by randomly switching off neurons like this, we force every single one that's left to become a strong, independent learner. It can't rely on its neighbors anymore. And this just dramatically cuts down on that co-adaptation problem and is one of our best weapons against overfitting. Another huge strategy is something called data augmentation. The idea is simple. If we don't have enough data, let's just make more. We can take the images we do have and create a bunch of slightly altered versions. Rotate them, flip them, maybe add a little bit of random noise. By doing this, we teach the model what features are actually important and what's just random variation that it should learn to ignore. Here's the thing though. All of these advanced techniques we've talked about, the cool optimizers, the dropout, they all rely on one thing, a stable training process. And that stability isn't something you can add later. It has to be built in from the absolute ground up, from the very first step. So let's talk about that first step. What happens if the network starting point, its initial set of random weights, is just terrible? So bad that the learning process can't even get off the ground. Well, this can lead to two pretty disastrous outcomes. First, you have vanishing gradients. This is where the learning signals get weaker and weaker as they travel backward through the network, until they're so tiny that learning just grinds to a complete halt. Or you get the exact opposite problem, exploding gradients. Here, the signals get bigger and bigger until the weight updates are just massive, chaotic swings, and the whole model just completely destabilizes. The fix, thankfully, is to use smart weight initialization strategies. You might hear names like Xavier or heat initialization. The analogy is perfect. It's like carefully setting up a really long line of dominoes before you push the first one. You have to get the spacing just right. These strategies make sure the initial weights are in that Goldilocks zone, not too big, not too small, so the signal can flow smoothly right from the get-go. On top of that, we also use a technique called batch normalization. This thing acts like a little regulator or a gatekeeper at the entrance to every single layer in the network. It takes whatever data is coming in and it recenters and rescales it before passing it on. This stops the data from shifting all over the place as the network learns, and it's absolutely crucial for keeping the whole process stable and preventing it from spiraling out of control. Now, what's really important to remember here is that all of these training principles we've covered, they apply across lots of different network designs, or what we call architectures. And just like in a workshop, for any given problem, you've got to pick the right tool for the job. And believe me, there is a whole zoo of these architectures out there. But the big three you'll hear about most are, first, convolutional neural networks, or CNNs. These are absolutely brilliant for seeing, for finding patterns in images. Then you have recurrent neural networks, like LSTMs, which have a kind of memory, making them great for processing sequences, like text or time series data. And finally, the real game changer, the transformer, which has completely revolutionized how machines understand human language. And you can get a sense of just how big the transformer's impact was by looking at the title of the paper that introduced it. The title was literally, "Attention is all you need." The authors were that confident in their new core idea, this mechanism called self-attention. And you know what? They were right. It completely turned the entire field of natural language processing on its head. And all of this brings us to one final thought. We've just walked through this incredibly sophisticated, powerful toolkit for teaching machines. We now know how to navigate these complex error landscapes, how to stop models from cheating, and how to build a stable foundation for learning. So really, the biggest question isn't so much how we teach AI anymore, but rather, what are we going to teach it to do next?